Good morning or good afternoon. This week we'll be starting with Chapter 3. Chapter 3 is on discrete random variables and their probability distributions. So where are we in the module? WST 111 is made up of 5 chapters. So far we have done 2 chapters. Chapter 1 is on characterizing a set of measurements and Chapter 2 is on probability. So we'll be using what we have learned from these 2 chapters for the rest of the syllabus. Now in Chapter 3, we will be looking at the concept of a random variable. We'll be introducing the concept of a probability distribution, specifically for discrete random variables. We will look at the expected values of discrete random variables, the moments and moment generating functions, the binomial probability distribution, hypergeometric, negative binomial distribution, as well as a special case, which is called the geometric probability distribution. And then lastly, we will have a look at the Poisson probability distribution. Okay, so in total, we have 1, 2, 3, 4, 5 probability models, and then the rest are just basic properties for discrete random variables. All right, so let us get into section 3.1. In section 3.1, we will look at the definition of a random variable. We will learn that there are 2 types of random variables. By the end of this section, you must know the difference between a random variable denoted by a capital letter and its possible value denoted by a small letter. At the end of the section, you should be able to define a random variable. You should be able to define a Bernoulli random variable, a discrete and continuous random variable. And obviously, you should know the difference between a discrete and continuous random variable. All right, so some key concepts that you need to take note of are sample space, which you've seen already in Chapter 2. Then you have a concept rule, domain, range, numerical event, and random variable. In Chapter 1, we have learned already that there are 2 types of data. We have qualitative or descriptive type of data, or you have quanti or numerical type of data. Under qualitative, we have 3 kinds, or we have 3 categories for qualitative or descriptive data. You could have nominal, non-numerical data. This is where you're naming, for example, the gender, city, country, or age group of a participant. We also have ordinal non-numerical data. This is where you rate, for example, a service or a movie, or you indicate some level of importance. Okay? Then you also have binary non-numerical data. This is where you have only 2 outcomes, for example, yes or no, or true or false. All right. If you do not have qualitative type of data, you for sure have quantitative or numerical data. Under numerical data, you have 2 types of random variables. You either have discrete random variable or you have continuous random variable. And in this chapter, Chapter 3, we will start with, or we'll have a look at discrete random variable, and Chapter 4, we'll look at continuous random variable. Okay, so suppose that you have done an experiment and you have your possible outcomes from your experiment. So whether you did an experiment which yields qualitative or quantitative, numerical or non-numerical type of outcomes, we know that methods of statistical analysis require that we focus on certain numerical aspects of the data, right? So even if you have qualitative or quantitative outcomes, you must always calculate the basic descriptive statistics, such as the sample mean, sample proportion, or sample standard deviation. So the concept of a random variable allows us to pass from these experimental outcomes to some numerical function of these outcomes. And we will look at the 2 different types of random variables: discrete random variable and continuous random variable. But in this chapter, again, we'll only focus on the basic properties and most important examples of discrete random variables. Now, the first definition in this chapter says, For any given sample space S of some experiment, a random variable is any rule that associates a number with each outcome in the sample space. So in mathematical language, a random variable is a function whose domain is the sample space and whose range is the set of real numbers. So the possible outcomes from your sample space, we will consider that as the domain for your random variable, and the set of real numbers we will consider as the range for your random variable. So again, if I read it again, it says in mathematical language, a random variable is a function whose domain is the sample space and whose range is the set of real numbers. So we will be moving from the different experimental outcomes to numerical values, or denoting the experimental outcomes with numerical values. Notation-wise, we will use capital letters or uppercase letters to denote a random variable. So you would see most of the time that we'd use random variable capital letter X or Y, or it could be any other letter in our alphabet. Mostly it's at the end of the alphabet, but it's any other letter. So in contrast to our previous use of a lowercase letter, such as small letter x, to denote a variable, we will now use lowercase letters to represent the particular value of that corresponding random variable. And we will use the notation capital X bracket S equal to some possible value for our random variable, meaning that the small letter x will represent the value associated with the outcome S for this random variable capital letter X. Okay. Let us consider an example. All right, so here it says, let random variable X denote the survival status of a randomly selected Titanic passenger. So if you look carefully, you see that I define a random variable X here using words or a sentence. So I'm describing a certain scenario or something of interest here. And we're looking, in this particular example, the survival status of a randomly selected Titanic passenger. Now the sample space here is, for survival status, is that yes, they survived the fatal voyage, maiden voyage, or no, they did not survive the voyage. Okay. Now, notation-wise, the outcome, yes, they survived. That's one of the outcomes from the sample space. The outcome, yes, they survived, can be denoted by a numerical value 1 when we're looking at the specific random variable x. Okay, so the numerical value 1 denotes the outcome, yes, while numerical value 0 represents the outcome, no. So the possible values for our random variable x is 0 and 1. And if you look carefully, we will write here a small letter x, which denotes the possible values of our random variable. And we'll say equal to, and in curly brackets, you will list all the possible values for our random variable x. If you look at another random variable, let's say we define random variable y as a passenger class of a randomly selected passenger again. The sample space for this research question, if it is a research question, would be either passenger would be in first class, second class, or third class. And so we can use some numerical values to denote these outcomes. So if a passenger is in first class, instead of typing out first class in your Excel spreadsheet, we will use numerical value 1, right? Instead of typing out second class, we will use numerical value 2. And here we have numerical value 3, which then represents the outcome of a passenger coming from the third class. So now the possible values for our random variable y, we denoted using small letter y, then equal sign. In curly brackets, you list all the possible values, 1, 2, or 3. The second definition of chapter 3, or in section 3.1, says any random variable whose only possible values are 0 and 1 is called a Bernoulli random variable. So if we have binary variable, which have, for example, outcomes yes or no, or true or false, where the possible values is 0 and 1, then we know that that variable or random variable is the Bernoulli random variable. Good. The third definition. A discrete random variable is a random variable whose possible values either constitute a finite set or else can be listed in an infinite sequence in which there is a first element, for example, or a second element, or a third element, or a fourth element, or a fifth element, and so on. So if you can list the different outcomes, either the list could be finite or it could be infinite, but there is a sequence and you know exactly what kind of possible values you can expect in your data set, then we would most probably say that that variable is a discrete random variable. On the other hand, if we have these two possible outcomes, if both of these requirements are met, then we will say that a random variable is a continuous random variable. What are these requirements? Okay. Firstly, it says if a set of possible values or a random variable is continuous, if its set of possible values consists either of all numbers in a single interval, all numbers, or if all numbers in a disjoint union of such intervals are possible, as well as the probability of observing exactly that specific value is equal to 0, then we will say that these two criteria, if they're met, they will be describing a continuous random variable. So for example, let's say you're looking at the interval 0 to 1. Okay, including or not including 0 or 1 doesn't matter. So let's say you're looking at this particular interval. Now, if the first condition says that all numbers within this interval, if it's possible to obtain any number within this interval, then it's leading us to the concept that our random variable is continuous, right? So any number could be, for example, 0.1111, or any number could be 0.11135689 something. So we could have a number that is made up of 4 decimals, 5 decimals, or 8 digits, or 9 digits. It could be any number between 0 and 1. So we know that there are infinitely different ways of writing down all numbers between 0 and 1. So it's not only just 0.1, 0.2 to 1. There are infinite numbers between 0 and 1. Okay? And the probability of knowing, of observing exactly that specific number, if that is equal to 0, then you would be describing a continuous random variable, if those two criteria are met. Okay, but in this chapter, we'll be looking at discrete random variables. Let us consider an experiment where you want to observe if a student will pass or fail a test. So in this case, if you have one student, your sample space here for the different outcomes would be yes, they passed the test, or no, they failed the test. Okay, let us define then random variable x, which would indicate, we'll say let the random variable x indicate whether a student passes or fails a test. So it's either yes, they pass, or no, they fail. You only have two outcomes here, all right? So the next step here after defining our random variable x using capital letter is to then define the possible outcomes or values, numerical values for our random variable. So if we have here the outcome p, then the possible value for our random variable x could be 1, or we'll let the possible value be 1 here. And if then you have outcome fail, then we will let the possible value be 0. In this case, since we only have two possible outcomes, 0 or 1, we will say that our random variable x is a Bernoulli random variable. And so x will follow a Bernoulli probability distribution. Since it's a Bernoulli random variable, it will follow Bernoulli probability distribution. Now, suppose that you're looking at 3 students, okay, and you want to see if the 3 students will pass or fail the test. Now, the outcomes for this experiment are as follows. So all 3 could pass, or all 3 could fail, or 2 of them could pass, or 1 of them could pass the test. Okay, so now if we define a random variable, we can define 2 or 3 different types of random variable from the same experiment. Okay, so the first random variable that we could define in this example is random variable x, which indicates the number of students who passes a test. Okay, so in this case, since we have 3 students, all 3 can pass, or 2 of them, or 1 of them, or none of them could pass the test. Okay, so looking at our possible outcomes, the possible values for our random variable x is as follows. So let us consider then the possible values for all of these outcomes here. So if we have then P, P, and P, 3 P's, then it means that all 3 of them have passed. If you have 2 P's and 1 F, it means 2 of them have passed. P, F, P, 2 of them have passed. F, P, and P, 2 of them passed. P and F, F, 1 of them passed the test. F, P, and F, 1 of them passed. F, F, P, 1 of them passed. And F, 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 none of them passed the test. So it means that our possible values for random variable x, denoted by small letter x, is equal to 0, 1, 2, and 3. So these are the only possible values for random variable x. Now another random variable that can be defined from this experiment is random variable w. In this case, it says there, let random variable w denote the number of times one would observe 3 consecutive passes. So if we have 3 students, that's experiment, how many times would you observe 3 consecutive passes, where the first student passes, second one gets a pass, and the third one also gets a pass? How many times would you observe this? We see that you could observe it once, right? So either yes, all of them pass, or no, none of either all of them pass, or another outcome where 2 of them, or 1 of them, or none of them pass their test. Okay, so we can then define a random variable, or say that our random variable w has only 2 options, right? So it's either all 3, you observe all 3 consecutive passes. We can denote that with a 1, that yes, you observed all 3 consecutive passes, or no, you did not observe 3 consecutive passes. So we can say that random variable w is a Bernoulli random variable. And w then follows a Bernoulli probability distribution. Okay, another example. Suppose that we look at the finishing times of a randomly selected runner, and we define random variable z as the finishing time for a randomly selected runner. Okay, so what kind of random variable is z? Is z a discrete or continuous random variable? Which one is it? What do you think it would be? Continuous? Discrete? Okay, let's see. So firstly, what would be the possible values for a random variable z? Can you determine in a finite set or infinite sequence what the exact possible finishing times could be? No, right? You cannot list them in a finite set or sequence, because we know that the finishing time is any time greater than 0 seconds. So it could be greater than 0 seconds and less than, let's say, maximum hours, let's say 5 hours. All right, to qualify or say that you have participated in a marathon, you should start between 0 seconds and you should complete it within 5 hours. All right, so we cannot list the possible times or possible values of a random variable z in a finite set or a sequence, because any time between 0 seconds and some maximum number of hours is possible, right? And you cannot predict that someone would finish in 1 hour, 59 minutes, 40 seconds, and 2 milliseconds. You cannot predict the exact finishing time because time is continuous. It goes on and on and on, right? So we'll say that random variable z, since it satisfies those two criteria, it is a continuous random variable. Good. Now let us consider exercise 6, which says starting at a fixed time. This exercise is in your textbook, by the way, in section 3.1. So it says starting at a fixed time, each car entering an intersection is observed to see whether it turns left, right, or goes straight ahead. So the experiment terminates. The experiment will end as soon as a car is observed to turn left. Let random variable x denote the number of cars that you observe until an experiment terminates. So what are the possible values for a random variable? List 5 outcomes and associated x values. So let us begin. Suppose that you're sitting there at a crossroad and you're observing or counting the number of cars that either they turn left, right, or go straight ahead. So suppose that the first car that you see turns left, so which means that the experiment would terminate or would end at that moment, the moment you observe a car turning left. All right, so that is one outcome. Or suppose that the first car turns right and the second car turns left. So for that particular day, you would have only counted how many cars? 2 cars, all right? Or suppose that the first car goes straight ahead and then the second car comes and then turns left. So at that moment, you would have observed how many cars? You would have observed 2 cars. Or another possible outcome, the first car would turn right, the second car comes and turns right, and then the third car only then comes and turns left. So for that particular time, you would have observed 3 cars. Then you would end the experiment. Or the first car would go straight ahead, second car turns left, third car then turns right, and then at that moment, you would have observed how many cars? 3 cars, since you have to end the moment the next car turns left, all right? So the infinite number of possibilities or outcomes, since you could have, let's say, first car that turns right, second car turns right, third car turns right, and then only the fourth car turns left. So you would have observed how many cars? 4 cars, since the experiment will end the moment the next car turns left, okay? Or you could have straight ahead, then turns right, then maybe turns right again, and then the fourth car only then comes and turns left, right? So you'd have observed 4 cars there. Or you could have right, second car right again, third car right again, fourth car right again, fifth car then comes and turns left. So, but on that particular time that you're doing the experiment, you would have observed 5 cars. Okay, so these are the possible outcomes. We see that we have infinite number of possible outcomes. And so the number of cars observed depends on whether the next car turns left or not, right? So we will say that random variable x will take on possible values 1 or 2 or 3 or 4 or 5 or 6, or the infinite number of ways, infinite number of outcomes for this specific experiment. Okay, so these are the possible values of random variable x. Now, if you list the outcomes and the associated x values, this is how you would list them. Okay. So the first outcome that we could consider is if the first car comes and turns left. So this outcome here will have a possible or associated x value for that would be 1, because you would have observed one car, right? Or you could have outcome RL, where the first car comes and turns right and only the second car comes and turns left. So you would have observed on that day 2 cars. Or you can have RRL, where the first car comes and turns right, the second one turns right, and only the third one turns left, and so that day you would have observed 3 cars. Or you could have RRRL, where you have 4 cars observed, or RRRL, you have 5 cars observed. So there are different possibilities. You could also try doing this using a tree diagram. Okay, so we have first cars here, either they turn left, right, or go straight ahead. If they turn left, then the experiment ends, right? And then you count until how many cars you would have observed until the experiment terminates or ends. Okay, so if the first car turns left, then you would have observed 1 car there. Or if the first one turns right, then you have to continue the experiment. The second one can turn left or right or go straight ahead. The moment then the second one turns left, you end the experiment there. It means that on that particular day, you would have observed 2 cars, okay? Or the first car could go straight ahead and then the second one turns left, or it can turn right, or it can go straight ahead. So the moment it turns left, you stop the experiment, and so for that moment, you would have observed only 2 cars. Okay, and then the other outcomes, you have to continue. If the first one turns right, the second one turns right, then you have to look and see, will the third one go left or right or straight ahead? So you will have, or you will see that you have infinite possibilities or different outcomes. All right. Okay, so that's it for section 3.1. Your homework, which is not for submission by the way, is to go through examples 3.1 to 3.6 and also do exercises 2, 5, 7, 8, 10 on page 100. You can do these, or make sure that you do these or practice them before the semester test. If you struggle with any one of the questions, do let us know on the discussion board, post the question there, and also remember to include your attempt as well. By the way, exercise 5, we've already done or answered here. So you can use the question or the scenario here with question 6 to help you answer question 5. So question 5 is asking if you have an infinite or if your sample space consists of infinite number of outcomes, then does it mean that your random variable that you define will also consist of infinite number of outcomes? Yes or no? All right, so it depends on how you define your random variable. If, for example, here our sample space consists of infinite number of outcomes, we can decide to define random variable W and say let random variable W indicate whether a car turns left or not. So you can define a random variable of your interest. It doesn't have to be specifically this type of random variable X. You can define it. In this case, if you define random variable W as to indicate whether a car turns left or not, then we know that W will have possible values 0 or 1, since there are only 2 outcomes. Does it turn left or does it not turn left, right? So W will say it's a Bernoulli random variable which follows a Bernoulli probability distribution. So we see that if you have a sample space that consists of infinite number of possibilities, it does not mean that a random variable that you define from that experiment will also have infinite number of possibilities. No, you can have a sample space with infinite number of outcomes, but with a random variable that has a limited or finite number of outcomes. Okay, good.